Hello everyone, welcome to this class on finite element analysis, and in this class let's solve problems on tapered bar, that is obtaining the displacement at the nodes for tapered bar problems. So here in this problem you have the question reads like this: find nodal displacements, stresses in each element and reaction of the fixed support for the thin plate of uniform thickness of 1 mm as shown. Take Young's modulus E equal to 200 GPa. Weight density is taken to be 76.6 into 10 raised to 3. In addition to the weight, it's subjected to a point load of 100 Newton at its midpoint. So here we are going to consider this as node number 1, this as node number 2, and this as node number 3. And here it is a tapered bar. It is not like a normal one. So previously we have solved stepped bars and also bars with distance gap problems. So compared to that, this is a different one, and here it's this is a tapered bar, and this tapered bar problem has to be converted into a stepped bar. So that is the first step whatever we are going to do. And the first, let's try to write the given data. The given data is given as E equal to 200 GPa. That is considered to be constant for both the elements E1 and E2. So E1 and E2 both will be 200 GPa. 200 GPa can be written as 2 into 10 to the power of 5 Newton per mm square. And here the length L1 can be considered as 120 mm, and length L2 can be considered as 240 minus 120, which is equal to 120 mm. And apart from that, this is nothing but the width is given. So width is given. Width 1 I will consider as 60 mm. Okay, before going into width, let me try to do some other things. They have given thickness as 1 mm, so try to include that also as a data. Thickness as 1 mm. Apart from that, they have given this one, density. Density is given as 76.6 into 10 to the power of minus 3 Newton per mm cube. So just look out for some other data. All the data you can just see it is either in Newton or mm square, mm cube. So just it is included like that. So now what we have to do is, the next thing is do the first thing, that is FEA model. So this tapered bar has to be converted into a stepped bar. That is the first step. So the first step will be FEA model. So the FEA model will be like, so this tapered bar will be drawn out as a stepped bar. So it will be drawn out as a stepped bar. I mean, this has to be converted into a stepped bar of widths W1 and W2, of width W1 and W2, not of this width. This width has to be converted into the stepped bar width, and this will be like length L1, and this will be length L2. And similarly later on after that, so this will have area A1 and this will have area A2. So in this problem we have to find out all those areas, widths and thicknesses. So now let's try to do the next thing. So first thing what we have to do is we have to find out the area of the element. So okay, to find out the area of the element, whenever this width is given, we have to first find out the width. So the thing is width of the plate at the center. So width of the plate at the center. So what is the width of the plate at the center? So this tapered bar is converted into a stepped bar, and in the stepped bar, what is the width at the center? At the center, so here it is given initially as 60 and here it is given as 30. So 60 plus 30 divided by 2 will be at the center. So 60 plus 30 divided by 2, 60 plus 30 will be 90, 90 by 2 will be 45 mm. So 45 mm will be the width at the center. Now you have to find out what is the width above this center and what is the width below this center. Above this center in the sense it is left hand side, and below this center in the sense it is right hand side. So what is the width above the center? So we are going to take, the formula is average width of the plate above the center. Average width of the plate above the center, that is going to be width W1. So that is going to be width W1, or for element 1. So that is going to be the 60 plus whatever is there at the center. 60 plus 45 divided by 2. So 60 plus 45 will be 105. 105 by 2 will be 52.5 mm. Now similarly we are going to find average width of the plate below the center. Average width of the plate below the center. Average width of the plate below the center. Below the center is in the sense it is to the right hand side. Average width of the plate below the center. So let's try to find the average width of the plate below the center. So below the center is nothing but it's nothing but going to be this 45 plus 30 divided by 2. So 45 plus 30 divided by 2. 45 plus 30 divided by 2. That is going to be 75 by 2. So the average width of the plate below the center is nothing but 45 plus 30 divided by 2, which is nothing but 75 by 2, which is nothing but 37.5 mm. So that is considered to be the width W2, and whatever we found above the center, that is considered to be the width w1. So now using this w1 and w2, we are going to find out the area of element 1 and element 2. So therefore the area of element 1 is going to be w1 multiplied by thickness. Similarly, the area of element 2, is going to be w2 multiplied by thickness. So w1 is 52.5 multiplied by 1, that is 52.5, and this is 37.5 multiplied by 1, that is going to be 37.5 mm square, and this is going to be 52.5 mm square. So the first thing in this problem is to identify these areas. So this is nothing but going to be A1, and this is nothing but going to be A2. And we have got L1 and L2. L1 is found to be 120, and L2, the whole 240 minus this 120, it's going to be 120. And E1 and E2 are going to be 2 into 10 to the power of 5. So using all this, now we are going to do the elemental stiffness matrix. We are going to find out the elemental stiffness matrix. The elemental stiffness matrix for this problem, it's going to be like K equal to A into E divided by AE, EE divided by LE, 1 minus 1 minus 1 and 1. So we are going to find out that. So K1 equal to A1 is 52.5. 52.5 into E1 is 2 into 10 to the power of 5 divided by L1, which is 120. So it's going to be 1 minus 1 minus 1 and 1. Similarly for K2, K2 is going to be A2. A2 is 37.5 into E2. E2 is 2 into 10 to the power of 5 divided by 120, which is the length. And here it's going to be 1 minus 1 minus 1 and 1. So first I'm going to solve this. So K1. So K1 10 to the power of 5, I'm going to just leave it here itself. Whatever this 52.5 multiplied by 2 divided by 120, that I'm going to multiply it inside. So all these things I have just solved it in the previous problems itself. You will be understanding it. So let me try to reset this calci. Okay. So now it's 52.5 into 2 divided by 120. So the answer is found to be 0.875. So 52.5 into 2 divided by 120. So it's going to be 0.875. That 0.875, I'm going to multiply it inside. I'm going to get this as the answer. So minus 0.875 and plus 0.875. And similarly K2 what I'm going to get is 37.5 multiplied by 2 divided by 120. I'm going to get 0.625. So 10 power 5, I'm going to retain it here itself, while 0.625 I'm going to put it here. So 0.625 I'm going to write it here. So now this elemental matrix 1, that is stiffness matrix 1, that is for nodes 1 and nodes 2. So node 1 and node 2, this is for node 2 and node 3. So this is going to be there for node 1 and node 3. Now we are going to do global stiffness matrix, that is GSM. So GSM, global stiffness matrix, is nothing but K equal to K1 plus K2. So K equal to K1 plus K2, when we are going to do that, we have totally of three nodes. Therefore K will be equal to, so 10 to the power of 5 will remain constant. So 1, 2 and 3. And similarly this is going to be 1, 2 and 3. So you know that well. So at 1 and 1 we have only 0.875. At 2 and 1 you have minus 0.875. So I have just told you how to add this elemental stiffness matrices many times in the previous videos. You can just watch it if you don't understand. So 3 and 1 is also 0. 1 and 2 is minus 0.875. Well, 2 and 2 is 0.875 plus 0.625. 0.875 plus 0.625. So that is found to be 1.5. Well, 3 and 2 is nothing but minus 0.625. 1 and 3 are not connected anywhere. 2 and 3 is minus 0.625, while 3 and 3 is 0.625. So this is nothing but the answers. So now you have to write the global nodal displacement vector. So global nodal displacement vector is nothing but going to be Q1, Q2 and Q3. So before going into global nodal vector, so global nodal vector, so that is for F, we have to do one small thing. For global nodal vector, we have to consider this weight density in this problem. So we have to consider something like this: elemental body force vector due to weight density. Elemental body force vector due to weight density, because of weight density there will be weight at every nodes, even at the nodes where it is fixed. even their weight will be there. So for example, here in node number 1 it is fixed, but even though here also you can expect some weight to be added. So that's what you say, elemental body force vector due to weight density. So the formula for that will be Fe equals to Ae Le into density I'm just going to write it as rho something divided by 2 and 1 1. So here I'm going to write it f1 and f2 is nothing but going to be, or else I'll just say like density is going to be like delta 1 delta 2, both are going to be equal to weight density. Okay, so they are nothing but weight density. Okay, now let me not take delta 1, let me just take it as rho 1, which is equal to rho 2, which is equal to weight density, and that is equal to rho. And even here let me change it as rho here. So now let's try to solve that. So here when I just try to solve that, so what I'm going to get is, so elemental body force 1, that is nothing but going to be A1 L1 into rho 1 divided by 2 and 1 1. So A1 is nothing but going to be area, that is 52.5, which we have obtained it earlier, and the length L1 is 120, and this density is given in the problem. You can just consider the density to be constant throughout, so therefore it's going to be 76.6 into 10 to the power of minus 6 divided by 2 and 1 1. So upon solving all this and multiplying that inside, you're going to get it as 0.241 and 0.241. Similarly, F2 we are going to solve it A2 L2 rho 2 divided by 2 and 1 1. So let's try to substitute all those values. We are going to get 37.5 into 120 into 76.6 into 10 raised to minus 6 divided by 2 and 1 1. Therefore F2 is going to be, so upon solving you're going to get a 0.172 0.1723 0.1723. So that is going to be the answer. So now this is for node number 1, this is for node number 2, similarly this is for node number 2, and this is for node number 3. So now we have to add all those things. Now F is going to be whatever we have obtained here. So at F1 you can just see in the problem clearly, F1 the node 1 is fixed. As node 1 is fixed, there's, the load acting on node 1 will be 0, but here you can see 0.241 in node 1, so that's what you're going to add, 0.241. And at node 2 you can clearly see that at node 2 a load of 100 Newton is acting, so therefore you have to consider that 100 Newton as well as, so here you can see at node 2 there is 0.241 as well as 0.1723. So both are available here. So all those things you have to add. And at node 3 you can just see in this problem no load is given, therefore it has to be 0, but here at node 3 0.173, because of weight density you have that. So let me just try to consider all those. So upon adding you get 0.241 100 point, when I'm just trying to add both these, I'm going to get 100.4133, and here I'm going to get 0.1723. So I'm going to get all these. So this is nothing but going to be F1 F2 and F3. So next I'm going to add this, next I'm going to consider this equilibrium equation. So next is equilibrium equation or equilibrium condition, let's say anyhow. So let's try to solve this equilibrium condition. So equilibrium condition is given by K into Q, which is equal to F. So we are going to consider K into Q, which is equal to F. So upon substituting all those values, we are going to get 10 power 5, which is equal to 10 power 5, which is equal to and 0.875. That is the value of the global stiffness matrix. So 0 minus 0.875, 0 minus 0.875, 0, 1.5, minus 0.625, minus 0.625, and 0.625. And the Q1, Q2, Q3, I'm going to write it here, Q1, Q2, and Q3. And finally F1, F2, and F3, I'm going to retain this here, 0.241, 100.4133, and 0.1723. So I'm going to include all those things here. So this is what we have got as K into Q, which is equal to F. Now according to this elimination method, now we have to apply the boundary conditions. So according to elimination method, node 1 is fixed. As node 1 is fixed, we have to delete row number 1 and column number 1. So row number 1 is deleted and also column number 1 is deleted. So upon deletion we get these remaining elements. So that remaining elements we have to solve it. So let me try to solve that. First let me try to write that. So 1.5 minus 0.625 minus 0.625 and 0.625. So I have written all those, and let me also write Q2 Q3 over here, and let me also write 100.4133 and 0.1723. So now I have to do matrix multiplication over here. So this cell, this first row multiplied with this first column, and also the second row multiplied with second column. So first element with first element and second element with second element. 1.5 into q2, 1.5 multiplied by q2 minus 0.625 multiplied by q3, and that is going to be equal to 100.4133. And similarly minus 0.625 q2 plus 0.625 q3, that is going to be equal to 0.1723. And here let's not forget to add the 10 power 5, and the 10 power 5 is going to be common to this. So finally, after obtaining the answers of q2 and q3, we are going to delete that, we are going to divide that answer with 10 power 5. That is going to be the, so this one you have to use this calci mode, where in calci mode you are going to take mode, equation mode in calci. So here in equation mode you are going to give, so let's give equation mode 1, and the number of unknowns are 2 here. So similarly you're just going to add that, you're just going to consider this as a1 b1 c1 a2 b2 and c2. So upon doing that, the answer whatever we are obtaining, that's what you have to consider. So q2 we are going to obtain it as, so q2 we are going to obtain it as like okay, let me try to just first put those answers. So a1 is found to be 1.5, while b1 is minus 0.625, and c1 is 100.4133, 100.4133. And let me also put the a2 is minus 0.625, and b2 is 0.625, and c2 is 1723, 0.1723. So finally I get the value of q2 as 114.956, that I'm going to divide with 10 power 5, and q3 I'm going to get the answer as 115.23, that I'm going to divide with 10 power 5, because that is going to be the final answer. So let me just try to divide the answers and just see 114.956 divided by 10 to the power of 5. I'm going to get the answer of our q2 as 1.14956. So that is going to be the final answer, with multiplied by 10 power minus 3 mm. So that is going to be the final answer, and for q3 I'm going to get the final answer as 115.23 divided by 10 raised to 5, and the answer is found to be 1.1523 into 10 raised to minus 3. So that is going to be the answer with mm. The SI units are going to be mm. So this is nothing but the final answers whatever we have got. So finally you can just write it, the global nodal vector as q1 q2 q3, and you can mention q1 as 0, q2 as this one, and q3 as this one. The next thing what you're going to find out is stresses in each element. Stresses in each element. So the stresses in each element is going to be similar as however we solved in the previous problems. So let's try to put the formula. Stresses is nothing but EE divided by LE minus 1 1, and this is going to be QI plus 1. So that is going to be the formula. And similarly when you are going to put sigma 1, that is going to be E1 divided by L1 minus 1 1, and that is going to be Q1 and Q2. So E1 is nothing but going to be 2 into 10 to the power of 5 divided by, and L1 is 120, and it's going to be minus 1 and 1, and for q1 we have got 0, and for q2 we have got 1.149 into 10 to the power of minus 3. So this is what we have got. And finally when we solve upon this, when we just solve all this and try to multiply it inside, the final answer that is obtained, okay, let me just solve it directly instead of just telling you the answers orally. So let me just try to solve that. So first let me just try to put 2 into 10 raised to 5 first within the brackets multiplied by 120, that is going to be 1666.67. So let me just multiply that inside. So I'm going to get 1666.67. Here it's going to be 0 and 1.149 into 10 to the power of minus 3. So this multiplied with 0 and this multiplied with this answer, it's going to be finally, so this multiplied with 0 is going to be 0 only, but this multiplied with 1.149 multiplied by 10 to the power of minus 3, the answer is going to be 1.915. So finally stress 1 value is 1.915 megapascal. That is the final answer whatever we have obtained. So stress in element 1 is 1.915 megapascal. So similarly stress in element 2, that is nothing but given as sigma 2, that is something but E1, that is Young's modulus in element 2, and length element 120, and it's going to be minus 1 and 1, and here I'm going to put q2 and q3 values. So q2 values are obtained here and q3 value is here. That is nothing but 1.149 into 10 to the power of minus 3, and here it's going to be 1.1523 into 10 to the power of minus 3. So upon solving this, I'm going to get the same 1666.67 only, that I'm going to multiply it inside. So that 1660 minus 1666.67 multiplied by this, and this is going to be, so I'm just going to get the answer as 1666.67. So this I'm going to get as 1666.67, that I'm going to multiply it inside. So therefore minus 1 into that is going to be minus 1666.67, and here it's going to be plus. And now let me just try to multiply this. So when I try to multiply this, so here I have to multiply this first element with this first element here, and second element with the second element here. So upon multiplication, the answer whatever I'm going to get is, so now let me try to multiply that. So upon multiplication, I get 1666.67 multiplied by 1.149 into 10 to the power of minus 3 plus 1666.67 multiplied by this, that is 1 point into 10 to the power of minus 3. So upon multiplication, the answer whatever I'm going to get here is, so let me try to add the answers. So here I'm going to get 1666.67 into 1.149 into 10 to the power of minus 3 plus, so just put, let me open the brackets, 1666.67 multiplied by 1.523 into 10 raised to minus 3. So the final answer is found to be, so I'm just getting the answer as 0.62. So 0.62 is the final answer. So 0.62. So let me just re-verify that answer once. So let me just put it as minus 1666.67 into 1.149 into 10 to the power of minus 3. So plus, okay, that is the right answer. So 0.623 megapascal or Newton per mm square. That is nothing but you're getting stress in element 2. Similarly, support reactions. So support reactions you have to do only for the element number 1. That is for node number 1. Only at node 1 there is a fixed support. Only that you have to do it. The support reactions formula will be K into Q minus F. So K is nothing but 10 to the power of 5. You get 0.375 minus 0.875. Here also here it's 0.875, and here it is 0, and here it is minus 0.875, 1.5 minus 0.625, 0 minus 0.625, 0.625. So apart from that, we also have like a q is 0, 1.149 into 10 to the power of into 10 to the power of minus 5, and here it is 1.152 into 10 to the power of minus 5, and here that is nothing but minus f is 0 0.241, 100.4193, and 0.711723. So here I'm going to just multiply these two matrices, reduce subtract with it. So I'm going to multiply only this first row with this first column. I'm not going to multiply the second and third rows because I want only R1. Therefore 0.875 multiplied by the 0 is going to be 0.0 only, and this third element multiplied with third element is also going to be 0 only. I'm going to multiply the second element, that is you have minus 0.875 multiplied by this 10 power 5 with 1.149 into 10 to the power of minus 5, that I'm going to subtract with 100.4193. So the final answer R2 or R1, I'm sorry, I'm going to just find out R1, but R1, so that R1 only I need. So R1 I'm going to just do it only here. So R1, the answer is going to be like, finally when I just substitute, I'm just going to get it like minus 100.568 Newton. So this is nothing but the reaction of the support. So I've just found out all the stresses, displacement of the nodes, and the reaction of the supports. I hope you understood this. Thank you.